In a previous video, I vocalized a question that was probably nagging a number of you, and that had to do with, like, what's the point of finding the area under a curve exactly? Well, my hope that example 7 is going to start paving the way to answering that question for us, and then also making some connections between the type of calculus that we were doing when we were taking derivatives and this new kind of calculus that we're doing. Well, we had antiderivatives, and now area underneath a curve. Okay, example 7, suppose the odometer in a car is broken. Remember, if you don't know, an odometer just measures how far you've traveled. It's usually the little numbers that are right down below on the speedometer. It's broken, but we still want to estimate the distance driven over a 30-second time interval. The table shows the speedometer readings for selected times, in this case, every 5 seconds. So first of all, if your odometer is broken, you're probably not going to pass inspection. Anyway, so let's say that you are illegally driving this car in which the odometer does not work. But luckily, the speedometer still does, and so while you were driving over the course of 5 seconds, you wrote down how fast you were going in terms of miles per hour. Okay, the problem with this situation, I mean, there's many, but one of them is the fact that you've got time in seconds versus time in miles per hour. You've got two different time signatures. Yeah, we'll go with that. So you need to convert them both into the same thing, and so it's a matter of doing a quick conversion here to turn this thing into seconds. Turn it into a seconds, though, is going to make these miles maybe obnoxious little decimal numbers. So instead, how about we turn them into feet per second? And so here is the same exact speed, our velocity versus time, but this time in feet per second. Okay. So the question is, like, how am I supposed to, I just have velocity and I have time. How am I supposed to get how far the car traveled over those times? Well, think about back in grade school, the distance equals the rate times the time equation. I can just multiply a rate times a time, a velocity times a time, and I should be able to get a distance. And what I'm going to do is I'm just going to total up distances over each of these 5-second subintervals here. Maybe it would be helpful if I quickly sketch out a scatter plot. Ta-da! Yep, there you go. And then, who knows, maybe this function is, it should be some sort of continuous function. We don't know exactly what the equation would be. It doesn't really matter. We just need the little points here. Okay. And let's see. So like I said, we're talking about this good old-fashioned equation, distance is equal to rate times time. And now think of this feet per second here as our rate, and we multiply it times our time, which is in seconds. Of course, these cancel out, and it just gives us feet back. So this will be a way for us to find the total distance that this car traveled, right? We're just going to add up each of the small little distances, but we'll have to make maybe a little bit of an assumption here. I'm going to write d is approximately equal to, so I'm going to assume that over the course of this first 5 seconds here, that the car was going 25 feet per second, and it stayed at that speed until it reached 5, and then it jumped up to 31. Is it realistic? Probably not, but we'll just go with it for the purposes of this approximation. Okay, so I'm going to say that for the first 5 seconds, that's going to be my time, the velocity of the car is 25 feet per second. So I would multiply my velocity, 25, times the time, 5 seconds. All right, so there's the first little interval. And then I have another little interval of 5 seconds. So in this next 5 seconds, let's say that we were going 31, a constant velocity of 31 until I got up to 10 seconds, and then magically my car jumped up to 35. Okay, so I'm going to say 31 feet per second that I'm going to multiply times 5 seconds. Keep going. The next 5-second subinterval, let's say that I was going 35 feet per second. What's going to be the next one? I would do 43 times the 5. Then I would do 47 times the 5. And finally, I would do 45 times the 5. Would I include the 41? No, because look at how many little subintervals I've got. I've got 1, 2, 3, 4, 5, and then 6, and that 6th one is going to end right there at the 45. And you can count these up and you can verify that I do have 6 of these little subintervals. Okay, so it would just be probably a fun calculator activity to just multiply and add up all of these distances in the calculator, and you would get a distance of approximately, I think it's 1,130 feet. Okay, all right, let's see if we can make some connections here. Let me move this out of the way first of all. I'll put it right. No, I'll put it, no, here, no, there. Yeah, we'll just put it right down there. Okay, so when I'm multiplying this 25 times 5, let's look at the graph right here. Here's the 5 that's right down here, and then here's the 25 along the y-axis. You know what you could do? I mean, if you wanted to, you could turn that into a rectangle like this. This would be like a rectangle right here. So basically that's what I just did, is like I found the area of a rectangle. Right, and then the next one would be 31 times 5. The 5 is down there at the bottom, and then I come straight over here and I make myself another little rectangle. Curious. And then I've got the 35 that I just drag straight over to make another rectangle. And then the 43. What's next? The 47. This one goes above by a little bit. And then one more up to the 32nd. The 30 seconds. So what did we just find there? We approximated the area underneath the curve specifically using the left endpoints. This was a left Riemann sum. We could just as easily have used the right endpoints instead. We could have also used like a trapezoid, set of trapezoids here in order to approximate the area underneath the curve. So again, let's see if we can make a few more connections. So when we talk about S of t as being the position equation, this one's position, which measures a distance for us. And then we have our v of t equation, which measures our velocity. What do you have to do to your position equation in order to get the velocity? You take the derivative, of course, right? But then if you have velocity and you want to work backwards in order to find the position equation, the distance equation, if I'm going to work in this direction, that one is integration. Integration is associated with this area underneath the curve, and you can see why in this specific example that it does. It just makes rectangles. If I'm trying to go backwards, in this particular case, it's easy to see with rate times time as this creating some sort of rectangles. But that is, oh, are you kidding? Here we go. But that is the relationship that exists whenever we're working backwards through integration in order to work from a velocity equation to get the position equation. But the same thing is going to be true about any kind of antiderivative. Working backwards from a function to its antiderivative, this integration technique has something to do with this area underneath the curve.